Welcome everyone to this afternoon set of lectures. We have Professor Patrick Peter giving his third and last lecture on bounces. Over to you, Patrick.
Okay, thank you very much. So I'm glad to not see you again, which is very bizarre again. But okay, I think I need to get used to that. So first, one information I've received a couple of questions in the Slack line. So I think there is a general thread, and then there are specific threads to everybody. So I replied on the one which is dedicated to under my name seemingly. So please go there as well. I think it's better to have independent threads probably. That's why they have been built, I suppose. And okay, so let me begin. I hope you see everything fine. And again, don't hesitate to interrupt at any moment. And I'm sorry, I should have erased this board before. Right. So now that we have discussed some quantum gravity ways to have bounces, now that we have discussed some properties, we have discussed some how to do that. I want to discuss why we want to do, I don't even see myself, I'm sorry. It's a bit bizarre here. Okay. And so I want to discuss a little bit as to why first. I will first begin by why a bounce. Why using bounces? And that comes essentially to trying to summarize all the problems of the standard model and to see how you can solve them in the framework of a bounce. As I said, you can always mix up a bounce plus a phase of inflation, but if you can do it only with one, it's even better. So there are a couple of things. Of course, I already told you many times that there exists a time in the standard model such that the scale factor goes to 0, and usually we can set that time to 0 because it's easier, because then in that case you're just saying that for the radiation dominated era you have square root t. So in general, in what follows, I will show you a couple of models, and there will be shifts in time. Please assume that they are here. It's just to show the behavior. So normally you put 0 as the origin of times and then you shift them. Right, because of the existence of a singularity, that actually implies that there exists a particle horizon. So a word about the word horizon. You have two kinds of horizon. So one of them is that there exists a particle horizon. So there exists a particle horizon implies that the integral from your initial time to wherever you are now, d tau over a of tau, this thing is less than infinite. There is, in a sense, this is a past horizon, right? Maybe you could call that a past horizon. Whereas there is the so-called event horizon. In cosmology, of course, these words are adapted to all the possible situations, but in cosmology, that would be a past horizon, and the event horizon in that framework would be the opposite. So to the final time, say, of t, d tau over a of tau would be less than infinite. So this is somehow, you see, you go to the final, so that's somehow a future horizon, right? And you very often see the word horizon, which is not always adapted. So in particular, so the particle horizon divides the particles that you have seen with those which you have not seen yet, right? For any given observer that lives at a time t, right? And so this leads to a horizon size, which is simply the scale factor times this thing. So you start your universe at ti, you go all the way to t, and you integrate 1 over a. So this is the horizon size, right? And So if you have, for instance, if you begin the universe with, say, radiation or whatever, you have a constant equation of state. So P over rho equals W, let's say it's a constant. Then you can calculate this thing. You know what is the solution for the scale factor as a function of time. So you can calculate this thing. And you find that dH is equal to, so that's 3, 1 plus W over 1 plus 3W. And then you have T. And then I'm assuming T positives, right? All through. And that's 1 minus Pi over T to some power, which is 1 plus 3W over 3 plus W. Right. And so clearly, you see that if you have set the initial time, say at the singularity, set at Ti equals 0, so then you get rid of that. And in particular, for W equals a third, you see that this is 2 times time. So the horizon, and actually that's why that actually the horizon now is becomes the opposite 1 over the Hubble radius, which you can calculate. So that's why some people tend to confuse the horizon and the Hubble radius, although they are completely different theoretical objects. Right. So the fact that this horizon is finite, as you know, I'm sorry to repeat these things, but it's always better to understand what it is we're talking about in details. So what happens, you've seen this drawing many times, but it's sometimes interesting to see again anyway. So basically, where you plot as a function, you plot time here. And so space will be here. And let's say that you have the last scattering surface here, and you have light cone. So that will be the Big Bang, right? T equals 0, that's the singularity, which I denoted by T bar earlier. And you see that if you look, sorry, if you pick up a point here and you have light cones, forward light cone here, and another forward light cone here, and then we are here, basically, now that's our position in space, and we have our backward looking light cones. As you all know this drawing, you find that these regions, of course, have never been in causal contact, yet we observe exactly the same thing on that. So you see the idea. I think it's better if you do that in redshift space, where you are, say, in the middle of the sphere. So this will be, so the drawing is going to be horrible. I'm sorry about that already. So that's where we are, right? And that will be the last scattering surface. And then you have another surface, which is, so that's with a redshift ZLSS. And I remind you that the redshift is defined by 1 plus z equals the wavelength of a particle at the emission over the wavelengths, the reception or the emission. And that's essentially the scale factor at the reception over scale factor at emission, right? And so you have, basically, when you draw this thing this way, that will be the Big Bang, right? And so what you look here, the equivalent of that will be that you look at this particular sphere, the angle which is subtended by this sphere, and that will be here. So this will be roughly infinite, and that's here. So that will be 1 degree. And so in other words, what you find is that the number of such regions, when you calculate within the standard framework, the number of such region is, so that's around 8 times 1 plus z LSS, and the power is 3/2. And that's around 10 to the 6, because this z here is 10 to the 4, right? So you expect to have 10 to the 6 completely unrelated regions of space. So that's the horizon, the so-called horizon problem, which comes from the existence of a singularity somehow. Now, that's the first problem. The second problem, and then I will discuss the solution. So maybe I should discuss the solution right away. So we all know how it happens in inflation, and I guess we'll explain that in details already. But now here, so you replace this, now you pick up, imagine that you have a phase of contraction When you have a phase of inflation, you know that inflation breaks the strong energy condition, so you must have W less than -1/3 for inflation. There is an equivalent W thing in order to solve this this thing where you have where you see the conformal Hubble radius expanding again. The same thing applies here, but now if you have a perfect fluid in a contraction, you will see that this perfect fluid, during the phase of contraction, to solve this problem, you need, say, something which would have an equation of, say, Wx. And so you rewrite these things. Of course, now we're having negative possible time, so you have to put, like, you know, things like that. And there is actually an absolute value here. And so anyway, and you see that if you put Ti sufficiently far away in the past, this Hubble radius, the horizon now can become as big as you want and much larger than the universe. There is a constraint in that, and you can see it here, is that now Wx here must be larger than -1/3. So even though inflation requires, to solve the horizon problem, inflation requires some kind of exotic fluid, a bouncing cosmology requires, oops. I'm sorry, something has gone wrong. Someone tried to interact on Slack. Sorry. So for a perfect fluid in a contraction phase, it has to be a regular non-violating conditions, non-sec condition violating perfect fluid, right? So that's the first problem, which is the most crucial. And of course, if you don't solve this problem, your whole cosmology is dead. So now, the second, and more interesting from the point of view of bouncing, is the flatness problem. So we can write it in two different ways. And that's what I will do. Oh, and by the way, sorry, I should have mentioned that for, in general, what you find, so if you pick up a Wx, say 1/3, which is usually assumed, or 0, what you find is that you need to have, in order to solve the horizon problem, you need to have, you define the same kind of things, like the number of E-fold, but that will be of, how should I call that, contraction, the number of contraction, which is now the log of the original size of the universe over, say, the end of contraction, right? So you expect that, so you're having something like that, right? For the scale factor as a function of time. And so you start, you don't know exactly where, but you start somewhere here, which is Ti, the initial, so that will be Ai. And then, well, you can even put that as A of the bounce, right? You can even put that here. So this number here, you can calculate in order that the angle over which you see the universe is larger than 4 pi, which is what you want, basically. So this requires that this n is larger than 60. No surprise, it's the same kind of number you find in inflation for the same reasons. And it actually means that there is a region before you really enter into the bounds where we'll discuss this number after that, but essentially that corresponds to a redshift here between these, the minimum redshift, say here, and what we are measuring now, which I will call, I don't know, a redshift of bounds, say, which will be like 10 to the 28. Right. So these are numbers, and you can consider that they are approximately similar to what you find in inflationary framework, which is normal because you want to solve the same problem in a sense. So it is really the same thing. So now the second problem is the flatness issue. So first, let me just remind you briefly what it is. And first, you can rewrite one of the Friedman equation in that form, right? It's the sum over the omega i's minus 1, which is, this will be omega total, and that will be called omega k, right? And this omega I, just to remind you, is just rho I divided by rho critical and that is h square of t0. So anything with an index 0 refers to nowadays, right? Over h square of t, and then you have an omega I of t0 as measured now. And of course, A over A0, again, this is the A0 is for now, and minus 3, 1 plus WI, and I have, assuming that I have WI for each species. Right. So this, when you evaluate that, there are various things which you can do. One of them thing is that if you take this equation into account to derive it with respect to time or to scale factor or whatever you want, to take into account the other equation for the other Friedman equation, you also take into account that rho dot plus 3h rho 1 plus w equals 0. You mix up all the thing and you end up with the following result, which is d omega k divided by d log a equals 1 plus 3w 1 minus omega k. So w now is the general thing, right? Just as it is in here. And omega k. And if w is constant, you can actually integrate that. And that gives you omega k is now equal to omega k 0, which we know what it is, it's measured. And I will write it up explicitly. And that's 1 minus omega k 0, 1 plus z. You can rewrite the whole thing in terms of the redshift. 1 plus w, sorry, 3w. And then plus omega k 0. And as far as I know, omega k 0 is constrained to be less than, say, 10 to the minus 2. I will give only rough numbers here. It's not the point of doing precision cosmology at this stage. It's just to understand the ideas and the issues. So when you do that and you apply these things and you can measure, you can find out that this leads to a constraint, which is that omega k at equal matter and radiation ought to be 10 to the less than 10 to the minus 5, roughly speaking, which is already quite some fine tuning. But then if you really want to go all the way back to, say, the Planck regime, then you find something that has to be of the order of 10 to the minus 60. And now you also really have a problem because you really don't know why that would be such a small number. Right. And so now let me solve that issue first. Yeah, I wanted to go into the others. Okay. From the drawing perspective, there is another way to see that, which is the following, which I find interesting and illuminating as well, which is that this omega k is essentially, as I said, that let me take the absolute value of that because the absolute value of k is irrelevant, right? That's a dot squared. So that means that d omega k by dt equals minus 2 k, and then you have a double dot over a dot cube, right? And so you see this in the general usual standard model. So this is positive and this is negative. So the overall thing is positive, and therefore if you plot say this will be 0, and then you plot omega k as a function of time. So basically wherever you start from, except if k is strictly 0, but as you all know, it's a set of measures 0 in the set of solutions, so it would be a little bit bizarre. It's hard to understand. But if it is non-zero, even if you start with something which is very close to 0, well, you will increase, or if it is negative, you will decrease in absolute value, right? That's the standard model for which you're having a non-accelerator. I'm not talking about the current expanding accelerating phase, but a decelerating phase of expansion. Then you see that you're having this, and the problem is, of course, that you started from, I mean, that's been quite a while, like 14 billion years, and you started wherever, and you end up with something that has to be less than 10 to the minus 2. So this is exactly what I drew here, right? Now, when you have a phase of inflation, the solution for this issue is pretty simple. You're just saying that inflation means A double dot is positive, while A dot is positive. So all of a sudden, these things become negative, and what happens is you can consider that the phase of inflation was before, and so what happens is that you started with anything, and then all of a sudden you have your phase of inflation that drives you all the way to zero, and then really, I mean, I should have plotted in a logarithmic scale, and you go really to amazingly small values, and so that eventually, when you start increasing again, well, by the way you reach now, you're still at the 10 to the minus 2 level because you have been driven to these kind of values naturally, spontaneously, and of course it works both ways, right? So that's the phase of inflation. But now there is, of course, another solution to this problem, which will be to do the following. You know, you want the ratio to be, you want this ratio to be positive. And it's pretty simple. Both can be positive as in inflation, but both can be negative as in contraction. So now you can ask that A double dot is negative and A dot is negative. You see, because it's the third power arriving here. And so what happens now is that I'm lost in my papers. And yeah, so what happens now is the following. When you plot, it's a slightly different drawing. It's the same, roughly speaking, but there is one crucial issue which makes it different. So what happens now is the following. So you start, as I said, so you're having something, let's say that omega k is positive, right? I'm just taking the absolute value of omega k, right? And I plot that as a function of time as well. And so I start here, right? And I have something which, as I said, was decreasing in the past. And when you plot this value for the bonds, you see, for the bonds, you're having 1 over A dot squared. So that actually diverges at the bonds, which is just because of the definition of it, right? You have A dot going to 0. If you have 1 over A dot, obviously that goes to infinity. So you expect something like that kind of behavior. And here we go. Right, so you see it's a little bit different from that, but it is different because of this bit, right? Apart from that, it's essentially the same drawing. And so you're having here, so the idea now is that you're having, let me just set up notations. So you're having T minus, and here you will have T plus, right? And so the general idea is, okay, you have a phase of contraction here. Omega decreases as much as you want. And then you manage in such a way that here it was small. You assume that it will be roughly symmetric. And then after the bounds, it will be still small, such that when it increases, and we are now, it is still less than 10 to the minus 2, right? So that's one way of doing. So let me be perhaps a bit more precise about that and how we do that. So as I said, now I'm assuming that I'm having, so I start with my AI, right? So I'm going to have the same number of e-folds from say, I will have like this n plus will be the log of AI divided by, sorry, n minus, here that's minus and plus by minus. And that's roughly speaking, of course, the same as the log of AI divided by A bounds. And that's therefore, roughly speaking, the n equals 60, corresponding to a redshift of 10 to the 28, right? And now I'm assuming that all these phases of contraction is dominated by a fluid, which, as I said earlier, is just a constant equation of state omega Wx. And this Wx can be, I mean, it can be radiation, it can be dust, it can be whatever you want, an ordinary matter larger than minus a third. Right, so I can apply the equations I had earlier, right? On that side, from here to there, I can find that omega k at T minus, I can calculate it, and I find, applying the same equations as earlier, I find that it is omega k at the initial time, which is here. And sorry, I'm gonna have to put that again. So that's omega k of T minus is, roughly speaking, you can approximate these by assuming that n is large, omega k at Ti over omega x at Ti. And then there is the redshift factor, which is A divided by AI, 1 plus 3Wx. Right. At the end of contracting phase, you have this contribution, right? And now, of course, at the beginning of the expanding phase here, let's assume, to simplify matter for the purpose of this lecture, but you can complicate matters as long as you want, as much as you want, and it's a nice exercise to do it. But let's assume that we are still in the radiation-dominated era, right? For the purpose of the calculation, just only one fluid. So you get the exact same calculation, but now in the other way around, and you get a T plus now is like omega k of T0. That's the same calculation I did earlier, over omega radiation, say, of T0, which is now, but then now this factor is just 1 over 1 plus z, and it is squared, right? It's exactly the same equation, right? You just propagate this into here, and that's into backwards in here. And I don't know, you can assume, for instance, that z here can be 10 to the 8, for instance, and that will be nucleosynthesis, in which case that will be 10 to the minus 15 or something like that. You know this number, right? Now, so you started with something which was whatever you wanted. You have a phase of contraction. You know it lasts more or less 60-fold, right? So you reach the redshift of 10 to the 28, and now you have to go through that. So now, in order to go through that, you can use exactly the same kind of equation. I mean, basically, the equation is the behavior of time with time is that. It's 1 over a dot squared. And then you can calculate what it is analytically by setting, like, okay, like I'm going to say that between T minus for T in T minus and T plus, I will set that the scale factor is, how did I write that? A bounds times 1 plus T over T, well, C, I don't remember what I called it C, but anyway, squared, plus then I have a beta times T over TC cube plus whatever you want, right? So by assuming this, Taylor expansion for the scale factor, I can now calculate the propagation of omega k between here and there. So you see here I calculate delta omega k being equal to omega k t plus minus omega k t minus, right? And I do the same here using this formula and plugging it in here, and I can find another one, and I find that therefore here in this case it is minus, am I right, is it? Yeah, minus 3/2 beta, that comes in here. And then where is it? Sorry, okay. That's TC divided by A bonds squared. Right, so now you just identify all these things. As I said, you plug in this n equals 60-fold and all that, and that gives you a constraint, which is the following. So you're having A minus, which is this point here, the size of the universe right before it bounces, essentially, over the initial size of the universe, 1 plus 3Wx, minus, you adding this in, 3/2 beta TC over A bounds squared, and you now put the constraint that will be 10 to the 6. This is the number of different uncorrelated, and over Z plus squared, right? So if you're adding that Z plus is essentially Z bounds is essentially 10 to the 28 corresponding to these n equals 60, then you end up with the and assuming that Wx equals 0 or 1, anyway, it doesn't change much, what you find is that at the end of the day, Tc ought to be less than or the other 10 to the minus 25 A bonds. So I should not actually draw something around that because it's not such a nice result, but that explains why people usually assume an instantaneous bounce. Its duration is actually much, much smaller than the minimum size of the universe. Right, but if you assume all these parameters, and of course this is, for instance, this is assuming that beta was of order unity, right? Then you may have a model, an underlying model for which beta is already 10 to the 6, 10 to the minus 6, 10 to the, and then in this case you would reduce, or 10 to the 6, sorry, then you would reduce tremendously these constraints.
Patrick, can I ask a question? This is Sriram.
Yeah, sure, of course, Sriram.
The number, the 60, number of E-fold 60 that you assume, often, in the context of inflation, that typical number is arrived at assuming slow roll and so on. In the context of a bounce, in contrast, when the large scale mode will be inside the Hubble radius during the contracting phase, etc., will depend on the details of the bounce, and therefore the number 60 may be different. Can you come
right? Yes, you're absolutely right. The number 60, which I obtained here, was just in order to ensure that you solve the horizon problem. So it is not related with perturbation. I mean, it is somehow related with perturbations, of course, but it's just the largest possible size. You just assume that you only have one enclosing solid angle. That the solid angle over which you see the surface of last scattering is 4 pi. That's the only thing.
Okay.
And but of course, I mean, you're right, but it's basically that means that the largest perturbation comes from only one region. That's the same, basically.
Okay.
All right. Okay, so let me see. So now I have the flatness and the horizon. And but you see, really, this is interesting because people were worried to begin with that, of course, you would never solve the flatness problem because you have an increasing, I mean, omega k goes to infinity at this point. So in fact, it works pretty well. And now there are a couple of other issues which I want to discuss. I'm realizing that I'm taking far too long, but okay. There are some issues I won't even discuss. We can have these discussions later, perhaps on Monday. I think it's Monday afternoon or evening or whatever time it will be for you or me. But okay, so there is the reason why inflation was invented to begin with. People tend to forget that, but the reason why inflation was invented is because of ground unified theory that was based on the construction using a semi-simple unifying group leading to the standard model of particle physics, and that will produce monopoles who would overclose the universe, and therefore that was an issue. And or you can have, or in general, using other kind of theories, Sasaki or whatever, you would have relics in general. And these relics are unwelcome because they overclose the universe. And one way of doing that, I mean, if you just get rid of them by a phase of inflation, you're quite happy. But I'm not going to discuss that. One way of doing that, of course, is to never reach the temperature at which you form these objects, right? In particular for relics. So if there is a maximum temperature during the phase of contraction, if you arrange in such a way that the maximum phase of the maximum temperature is lower than, say, the gut phase temperature or whatever, then you may not form these relics. But there are other problems, and I'd rather not discuss them. But we can discuss them if you're interested in like on Monday. Another issue which is often mentioned is homogeneity. I mean, we're seeing an isotropic universe. I will go to that later, but we're also seeing a homogeneous universe. So in inflation, inflation solves that by saying that you start with a very small patch originally. Well, it's more complicated than that. It can be more refined than that. But essentially, the idea is that you start with a very small patch, which inflates, and therefore it's less problematic to have a small patch homogeneous than to have a big universe homogeneous. So inflation is that just using a small patch. Again, that's really in quote because this is far more elaborated than that, the true things. Now, in the bonds case, you can say, well, it's going to be even worse. I mean, because you start with a large universe that contracts, but then you can think of another mechanism which is compatible with all we said earlier, which is diffusion. I mean, we all know that in a room, there is a force of gravity that pulls everybody down, yet the air is roughly homogeneous in the room. And there is a reason for that, is that the diffusion time is actually much less than, say, the Hubble time, or I mean, the gravity time in our thing, but in the room. But the diffusion, if you have a diffusion time which is much less than the contraction rate, which is, again, one more reason to have a slow contraction, then you see that particles have time to diffuse on one another, and you end up with a homogeneous configuration if the universe lasts sufficiently long, right? This kind of thing also, I think, is a problem for cyclic models, because you need, essentially, if you have one bounce, you solve these issues, but if you have many bounces, it's not that clear. Right. Last of this simple matter is the Transplantation problem. It's pretty clear, and in particular, it's an issue. It's more of an issue for how should I say this? For inflation. The thing is the following. Again, I think, yeah, again, as a function of time, if you have a phase of inflation, you look at different scales, and the phase of inflation would have that will be the Hubble radius, right? So the Hubble radius will be roughly constant during a phase of inflation. That's the definition of phase of inflation. And then you transition to radiation, right? And then what happens is that if you give a look at whatever scale wavelengths here, you go backwards, so the wavelength goes essentially like that. But when it enters the phase, the inflation backwards, it goes exponentially to 0, right? Because it's just proportional to the scale factor. And then you can compare that with the Planck length. And then, so you see, normally you set initial condition in vacuum, but then you're setting initial condition, for instance, I mean, if you're setting initial condition here, you probably can assume that you are in vacuum because you are super Planckian, there is no problem. But why would you do that? And the issue is, of course, you could go backwards in time, and eventually you are reaching a point where, if you're there, is that for whatever value of the wavelengths you're going to consider, even the full size of the universe, for whatever L0, then you can write that L of t, which is L0 times A of t divided by A0, right? And this L of t may eventually be less than the Planck scale. And that's an issue because you don't know what the Planck, what the theory at this scale is. I mean, you can write things like I did in the first lecture, but it still is very complicated, and you have an issue here. You don't really know how to treat that. And so in the bouncing scenario, however, this is much simpler, because you see now you can plot, if you do the same plot as a function of time, you now plot the Hubble radius. So the Hubble radius is 1/h, and you know that again, h vanishes at the bounds by definition. So the Hubble radius is doing like that, and is roughly symmetric. I don't know if it is exactly symmetric, but anyway. And so that's h to the -1, the Hubble radius. And now if you pick up whatever wavelength, well, it can be you know, proportional to, I don't know, I mean, this is badly drawn, of course, but whatever wavelength is proportional to the scale factor, and the scale factor is actually bouncing. So you should shift that, I'm sorry for my drawings. And because the scale factor is bouncing, then you can just assume that now this is L Planck, and your wavelengths never enter in the trans-Planckian regime. And so you solve that pretty easily again. And fine, so I think we solve all the problem of the standard model. So basically, you pick up the standard model, you solve everything, you're happy. Well, I'm actually cheating a little bit because there is one bit which you haven't solved, and we haven't discussed that, because normally in inflation, you hardly discuss it. You hardly discuss it at all, because it is solved extremely naturally. And in fact, even in an ordinary expanding universe, somehow you expect to solve that. And it is the question of isotropy. And isotropy, by isotropy, I mean the shear, basically. So the idea, now the problem is the question of shear. Okay, to study the question of shear, you start with a universe which is, instead of, you replace Friedman, Lemaitre, Robertson, Walker by so-called Bianchi universe. And so if you want to be general, you should study all the Bianchi's universe, and in particular, you should study Bianchi 9 that has curvature in it. I'm not going to do that in this framework, but nothing essentially changes when you do that. So you can, in that case, you have curvature, but you will reduce attention to Bianchi 1, which is simpler. And Bianchi 1 is simpler in the sense that if you're writing ds squared equals minus dt squared, plus now you're having a of t, and then you're having a dx squared, which is now exponential to theta x dx squared. You have three privileged directions, right? 2 plus exponential to theta y dy squared plus exponential to theta z dz squared, right? And when you do that, of course, you have defined the overall scale factor. So you're saying that theta x plus theta y plus theta z equals 0. Right. So now you plug that into Einstein equation, like again, and you find the following. So you find h squared equals the third row, as before, plus 1/6 over the sum over I of theta I dot squared, right? And of course, you write that in the form of 1/3 rho plus rho theta. And the rho theta is simply 1/2 of theta dot squared, right? And then you have h dot now equal to minus 1/2 rho plus p, the ordinary fluid, minus 1/2 of the sum theta I dot squared, right? And now you can, well, you have two options. Either you differentiate that with respect to time and compare with this one, and you end up with an equation. You end up with an equation for theta I, which is theta I double I dot I plus 3h theta dot I equals 0, and that is telling you that theta I dot is proportional to 1 over a cube, right? And that gives you that, therefore, what I called rho theta, which was 1/2 of the sum of that. That's rho theta is proportional to 1 over a to the 6. Either you do that, or you do say that this thing is, okay, so it's minus 1/2. So this thing is equal to rho theta plus p theta, which is telling you that rho theta equals p theta. It's the same thing. You see, I have rho in the shear equals 1/2 sum over I theta dot squared, and it is p in the shear, and rho equals p means w equals 1, and w equals 1 again gives you back that the behavior is 1 over 6, right? So that seems to be fine. But the problem is that when you do that, you see the issue is the following now. you start with this universe, and in fact, it looks pretty much, from the point of view of the equation of motion, it looks pretty much like ordinary Friedman universe with an extra component which scales like 1/6. And the problem is that when shear dominates, you have an instability, which is the so-called BKL instability. I can give you references on that. I will not discuss that. But basically, if you start with this instability, you end up in a singularity. There is no way out. So you better not do that. And that's common to all the bouncing scenarios, that you have to avoid singularities and you have to avoid instabilities everywhere. And now when you do that, you see what if you want to avoid that, the issue is the following. You have the matter which scales like a⁻3. You have radiation that scales like a⁻4. And now you're adding the shear that scales like a⁻6. But when the scale factor goes down, eventually that thing will dominate over anything else. And so there is no issue. If you start only with matter, radiation, and any kind of, however small quantity of shear, you end up with a BKL instability and you end up to a singularity, even though you were pretending to solve that. So you haven't solved anything at all and you have an issue. And you see the problem, of course, if you have a phase of inflation goes the other way around, because when you're diluting matter, you're diluting radiation, but you're diluting even faster the shear. So the shear issue is not at all an issue in an expanding universe in a way. So now there is one other solution. The first trivial solution which you can think of, which is the so-called Ekpyrotic solution to that. So the Ekpyrotic solution is to assume that there exists an extra component, say based on the scalar field or whatever you want, but which is such that it provides you with a W phi, an effective equation of state, which is much larger than 1. And you see now when you do that, with W much larger than 1, what happens is that you're having this rho phi proportional to a⁻3, 1 plus W phi, as usual for everybody. And this is W phi is much larger than 1. This is much larger than 6. And that becomes much larger than the shear. So you start with something which does have an important shear to begin with, but then which is dominated by matter, radiation or matter. And then eventually this shear becomes dominated by that thing. And so you solve the problem. Now, of course, you can always argue that, yes, but at some stage, you have to go from this Ekpyrotic contraction to the bounce itself. And we know that the bounce itself must have 1 plus W negative, because it's the violation of the null energy condition. So we know that we cannot have W much larger than 1 at all times, because W must be of the order of -1 later. So the idea is to implement a phase where you have the Ekpyrotic contraction, and then you have the bounce, and you don't want the bounce to last too long, because otherwise you could get back to this problem, which is fine, because that's exactly what we said earlier. We don't want the bounce to last a long time, and it doesn't last a long time if you want to have a correct model. So let me now move to model, unless there are questions. Let me now move to the model. Specific implementation. Yeah.
I can ask if there are questions. Are there any questions? Please raise your hand.
So either I'm very clear or I'm very boring.
So that there are no questions as of now, Patrick. So
good,
please.
Excellent. So now I will proceed for the last, yes, slightly over half an hour, how I am actually implementation, not with actual theories, but with model, right? i.e. with fields. How can I do that? So the first model which you can think of, you want to, you see, and remind you that you want to violate the null energy condition. And you know that if you have a scalar field phi, you end up with rho plus p equals phi dot squared, which is positive definite, right? So the simplest possible idea you can have would be like to consider, say, a ghost field. That will be the so-called quantum model or Lee-Wick model. And the idea is that you now start with a Lagrangian that has two fields, phi and psi. And so phi is just a normal one, minus d phi squared minus v of phi, right? And now you take something which is different, and you get plus 1/2 of d psi squared. So the only difference is this sign here, and that's a ghost field, right? And because it is a ghost field, you can immediately calculate that it's rho plus p associated to psi is going to be equal to minus psi dot squared, right? So in other words, the full for this model, you will end up rho plus p equals phi dot squared minus psi dot squared. And then, so now this is no longer positive definite. And so you can start in a configuration when phi dominates in its potential. So very often what you do is that you assume a potential which is, say, 1/2 m squared phi squared. And you look at oscillations in these potentials. And because you're having oscillations in this potential, that's going to be like the density of rho far from the bounds, of course, on average. So yeah, it's going to behave as a to the -3. That's roughly, and that's an almost matter-dominated universe, or you can replace that simply by matter itself, matter fluid. But you see, eventually, that thing starts dominating. You swap the sign, and then you have the bounds, and then you're supposed to be back to the original. Now that's cool. That's a nice way of implementing things, except it doesn't work because, again, no surprise, that's unstable and in an unsolvable way. So you have instabilities, but that's the idea. Now you can, but still we can do something more along these lines and try to violate these null energy conditions somehow dynamically. The problem with this field is that it's violating the null energy condition at all times. So the overall null energy condition is violated only for a certain finite amount of time, but the specific one is violated at all times. So what you want to do now is imagine another way, which will be, let's assume that you have, sorry, a Lagrangian, which is now just a function which I call P because it's going to be equivalent to the pressure P of X. And now X is equal to -1/2 d phi squared, right? So when I have that, you can write, and yeah, okay, so defining P comma X equal dP dx, you find that the density corresponding to this thing is equal to 2x P comma X minus capital P. And then you can assume, now you look at this function and this is an arbitrary function, right? So because it is an arbitrary function, you can assume that there exists an xc, say, such that P comma X at xc equals 0, right? So you can, basically your function as a function of X, P of X, you assume that there is whatever, but there exists a point xc at which the derivative is vanishing, right? So if the derivative is equal to 0 at this point, then there is a region, which is that one, of course, during which P comma X is negative. And so in this regime, and I mean, I don't know, I mean, I wrote it like that, but it can be, you know, whatever. But there exists a range of X in which this P is negative. And so in this regime, you will violate the null energy condition. So in this regime, you can have a ghost and a bounce. And that is actually called ghost condensate. And so the idea now is that you start with a regular phase, you start here with your field, you make it evolve around there, you reach the ghost condensate point, you're going around this line, and then whatever happens, eventually you go back there. So for a finite amount of time, you're having a ghost, and it's not an intrinsic ghost. It's just because it condenses into a ghost. It's, in a way, you can see that as the equivalent of the Higgs mechanism, but now for the kinetic part rather than for the scalar part, right? So just to mention, there are a couple of models which are based on that. And yes, sorry, I should have said that. Therefore, yeah. So there are a couple of models. So there are the so-called K bonds, because in fact, this is the same, except for the ghost condensate, but it's the same idea which is used for K inflation. So that's why it's been called K bonds. Then you have the so-called new Ekpyrotic, because the Ekpyrotic model seems to be following the rules of, there was the old inflation. I mean, inflation ended up being old inflation and new inflation and whatever. And so the same applies to Ekpyrotic. And then there is also the matter bonds, which implement these things. So all these models, however, unfortunately, the conditions that have to be respected for these fields are very drastic. And so you can have a bound, but then you find some other issues. And in particular, there are, again, some instabilities coming in, unless you, I mean, I'm talking about simplest possible model, right? But if you start with only that, you have, again, instabilities. And in particular, they're due to the fact that there is no stable Poincaré invariant vacuum. And that is, of course, problematic. So if you're doing only with your kinetic term, it's not really working. If you're doing with a simple scalar field, it's not really working, as I explained, because it's almost impossible to get a bouncing solution. So the idea is to try to have it, to mix things, right? And so you get the so-called, I really don't want to enter into too many details, but there is this so-called Galilean ghost condensate model. So you take advantage of the fact that there are more than simple canonical terms nowadays. And so you're having a model which is Galilean and ghost condensate. And sorry, so for this, you will take an arbitrary function of phi and x, the same x as defined earlier, plus an arbitrary function of phi and x times box phi. And then to that, you can add whatever you want, perhaps like a dust pressure or whatever. So that is a much more general model. And I want to discuss this model a bit. So, okay, so this G function can depend in general of phi and x, and there are constraints on phi and G and phi and x derivatives. But the simplest possibility is to take it equal to a constant times x. This is not a canonical term because it's multiplied by box phi, right? And now for this one, there is a nice way to implement the ghost idea, and it's this way, which is you're writing it as, sorry, g of phi times x plus beta x squared minus a potential, right? And now you pick a g of phi, which is as a function of phi. You pick this g of phi here, and you pick some function which is such that, okay, let's assume it has this particular shape, right? Whatever, just a general idea, which is such that 1 is here, so that there exists a regime for which g of phi is larger than 1. And you see you're doing exactly the same as before, but it's in a simpler way in a sense. So you will be moving with phi. We can manage to build a theory such that phi arrives over here. Then phi goes across that. So normally what will happen is that it will go across and go down again, right? Depending on the shape of the potential, which I will draw later. And then you start, and then all of a sudden, this regime is, of course, the ghost regime. But it's just like in the previous case, it's actually a ghost condensate regime. Condensate. And then in that particular regime, you will rho plus p negative. You will be able to, so you are violating the neck, and you're able to produce a bounce in this particular regime. Now you have to make sure, and so this term is also added to ensure stability for the whole thing. And now you have to make sure that the potential admits these kind of solutions. And so you fix a potential which is, so as we discussed the other day, which has to be negative, in fact, and you say you pick up something which is something like that. It resembles the one I drew for the Ekpyrotic scenario. Right. So in practice, the idea is to write it as g of phi will be like a g0 divided by, so there would be a 1 exponential minus, sorry for the numbers, 2 over pi phi plus exponential plus like the coefficient bg 2 over pi 2 over p, so p, sorry, phi. And then you have the potential which is equal to minus v0 over something similar, minus 2 over q now. I'm picking up the same notation as in the original Ekpyrotic scenario, plus that you're adding extra terms just to make it smooth and nice, right? And that's plus 2 over q as well. Then you have a b, v, phi, right? And the idea is that p and q are supposed to be smaller than 1. Right. So now, if you pick up a solution, it's the situation where now if you're setting yourself in this regime, right? So I'm having phi large in amplitude, but phi negative. That is this regime. I can see immediately that the potential now is V becomes the Ekpyrotic potential, which is minus V0 exponential minus 2 over Q times phi, right? So because I have an exponential potential, if I neglect a couple of terms, but just to set up the thing, if we were in a general ordinary theory, scalar field theory, within this potential, I know that the equation, the Klein-Gordon equation, will be 3h phi dot equals minus dv d phi, and that would imply that phi would behave as square root 2q logarithm of v0 over q1 minus 3q t, right? So that's what it would imply. So I would have this solution at this stage. And if I were to do that, I could calculate, you see, the pressure associated to phi and the energy density associated to phi. And if I do that, I end up with being able to define W phi, which happens to be, in this case, minus 1 plus 2 over 3q. And if q is much less than 1, then this is much larger than 1. So this is the Ekpyrotic phase I'm looking for, right? So I can implement this Ekpyrotic phase pretty easily in here. And if I have that, then I know that the scale factor behaves as, well, I mean, a negative time thing, so minus t to the p, and H equals P over T. Right. So if I have that, I know that I have my Ekpyrotic contraction, right? Then I know that I have my ghost condensate. So basically I can reproduce everything I want, and I can build a complete scenario, which will be the following. So first I start with, as I said, I'm having the fluid here. So I start with a matter contraction, but I can have this contraction led by something else if I want. But I start with pressureless contraction. That will actually produce a scale invariant spectrum of perturbation, right? That would be NS of order 1. And as I said, you can range a little bit things in order to make sure that it's actually slightly less than 1, right? I remind you that the data we want to observe is NS equals 0.96 or something like that. Okay, then after this contraction, so then I produce the spectrum of perturbation, and I'm not interested in that anymore, right? Then I have the Ekpyrotic contraction. That one produces the spectrum, P zeta K, which is okay with the data, say. Then I have my Ekpyrotic contraction, and my Ekpyrotic contraction permits to remove any initial shear contribution, right? Then I have the ghost condensate phase. That's the bounce itself, right? And I can calculate exactly what's going on in this case. And it so happens that at the end, I end up with, okay, I have a fast roll. That's a consequence. Fast roll kinetic domination. Kinetic domination. And by this, I mean that at the end of this phase, I'm basically around here. So I'm having V much less than phi dot squared, which implies W phi now goes to 1, and that A goes to T to the 1/3. So here, in other words, here I was having A goes like T to the 2/3. And here I have A almost constant, very slowly decaying. And here I have the actual bounce, and then I have T to the 1/3. And I can connect the dots and build a completely satisfying model. And you can check that indeed the shear is removed in this regime. But of course it will grow again. But if you settle the parameter reasonably, you find that it will grow, but only slowly. And in fact, when the shear gets back again, basically it goes down again because the bounce is already passed. And so you have a nice and complete model.
Patrick,
well,
can I ask a couple of questions?
Sure.
The CMB scales are generated during the original matter phase, in the initial matter dominated.
Yes, absolutely.
Okay.
Yes.
Now, but we throw away other simpler matter models saying that they are unstable. This phase will still be unstable, correct?
No. This phase is not going to be unstable. Well, first of all, I'm saying that you can have a hydrodynamical fluid to use it, but of course I will discuss this instability later. But you can assume that it is a scalar field rather than a hydrodynamical fluid.
Nevertheless, a matter bounce I thought was not an attractor.
No. I know. But that's not the bounce. The bounce itself is taken care of by the whole the rest of the thing. You are having just this. So you're having just the contraction. The matter field, the matter domination here is just to produce the scale invariant spectrum. But then you go away from that. I mean, you want that, of course. You don't want to remain in this regime.
but matter contraction, even if it doesn't lead to a, not close to the bounds, still is not an attractor, correct? Or have I misunderstood?
I'm not sure I understand what you're saying. If you're having the whole thing just dominated by that.
Exactly. That will be not an attractor.
Well, what can it be? What else can it be? It's not an attractor in the sense that all the fields will take over it after,
okay.
For sure. But then if this is dominating to begin with, it is dominating. It's the only thing in play.
Okay.
Maybe we misunderstand what we're saying.
No, in the sense that if there are small deviations from that part, it'll just run away from it. That's the point.
Of course, that's exactly what I want. Because I want to enter the Ekpyrotic contraction before I reach the bounds. Otherwise, I go all the way to a singularity.
Okay.
And I really want to avoid that. So that's why I'm adding all these extra things. And the perturbations that are going to be created, you're saying that the perturbations may back react. Is that what you're saying?
No, my feeling is that if I have small deviations, if something, background density, there is a small deviation from what should be matter, then it will, run away from the matter contraction.
Absolutely. Yes, indeed, it will. And that's exactly the point. And as I was saying, we want that to happen because otherwise that's how Ekpyrotic contraction takes over. Because otherwise Ekpyrotic contraction would never take over.
Okay. But when you have these two fields, won't the ekpyrosis produce too much of entropy, isocurvature?
Oh, yes. I will discuss that after that.
Okay.
Yes, of course. I need to enter into perturbations now. I have 20 more minutes to enter to perturbation. Fortunately, David once gave lectures on that, and Will as well. So, but yes, of course, you have all these extra complications at this stage. So, but it was just to show how you can build a complete model that that satisfies more or less all the constraints, right? At least at the background level. And indeed, so now I need to move to perturbations. I should have done that earlier, but as I said, since I realized that David Wands and Will Kinney were talking about perturbation theory and inflation, I didn't need to go into these details, which is fine. So I will enter straight into the perturbations by going directly with the Mukhanov, Mukhanov Sasaki variable, which you know, I guess you know, since you have followed David Wan's lectures, that it satisfies this equation, z double prime over z, vk equals 0. And so this is 1 for ordinary scalar field, but it can be different if it's not an ordinary scalar field. And z, this equal a phi dot over h, which is referring to what you were saying the other day, that it has this rho plus p possibly going to infinity here. Right, and so basically, when you have the full complete model, then you can write on this is just a function of the background, of course. And so you have the full complete model and you write down, just to summarize what happens, as a function of now conformal time. Usually this thing, so in various models, you just build part of it. And so you're saying, okay, it's increasing like that, and then you are producing your perturbation and so on and so forth. In the complete model, well, you will have something like that. And so what happens with these perturbations, so let me write it this way here, z double prime over z as a function of eta. And what happens is that you put initial conditions here. So let me, well, since I have colors, I can use them. And I will have like, okay, that's k squared, potentially with ca squared, right? So ca squared could actually be also a function of time. So this could change. But in the general case, in the simplest case where k, the ca squared is a number, then the wavelength is that. So you see that for in this regime here, we are k squared much larger than z double prime over z. And so we can solve this equation extremely easily. And so we can set initial conditions for that. And usually we quantize the theory and we pick up vacuum, Bunch-Davies vacuum initial conditions. And that is telling you that you're having like Vk is e to the minus ik eta divided by square root 2k. That's the normal vacuum, quantum field vacuum normalization. And so you see that here you're having something which is oscillatory. Then in this regime, you see that now it's the opposite regime. You're having z double prime much larger than k squared. And now you can, because in this regime, you can also solve this pretty easily. You find that Vk now in that particular regime will behave like, that will be Z plus, let's say that's a number, depending on K, of course, plus another number depending on K, Z times the integral d tau over Z of squared of tau all the way to eta plus all the k squared term, right? So you can plug that and you look at what they look like, and you see that essentially one of them is growing, the other one is decaying. You have a growing mode here and a decaying mode, right? And so you're having this, sorry, so you start with here, so let's say you're having something like that, right? And eventually you end up with something which is roughly flat, and then you're back to the previous thing, but now you have mixed the exponential minus I and the exponential plus I, so you end up with a cosine here probably, or a sum of sine and cosine, and then you have these extra things, and then you will see oscillations in the spectrum at the end. Right, so that's a very brief 5 minutes summary of perturbation theory. And so that this is for the scalar mode, and the tensor mode is exactly the same thing. Basically, you're having mu double prime depending on k, plus now you have k squared minus a double prime over a. Now it's purely the scale factor mu k equals 0, but you see the overall thing is exactly the same. Now, one thing which is usually not mentioned in usual textbook on that matter is the vector mode. So the vector mode are not interesting in general for various reasons. One of them is that it's not dynamical. It's not, unless there is a specific vector source, but in general, it's not dynamical, and it behaves like 1 over a squared. So basically, if you start with whatever, you have 1 over a squared. So if you have a phase of inflation, of course, that thing just goes away, and there is no issue, no particular issue. Here, you find that the velocity of the perturbation happens to be proportional to k squared a to the 3 w minus 1. And in fact, when the universe is contracting, that could be an issue. So if you start with, by chance, you couple that to something to make it somehow dynamical, and then you put initial vacuum conditions, it's not going to grow too much, and it should not spoil the overall situation, but sometimes it may. And so some people are saying that, okay, that may actually spoil, again, the overall bouncing mechanism. But there is another way of seeing that, is that, well, this is a vector here. And so you can create some Lorentz symmetry breaking or isotropy symmetry breaking, but in a way which you see on average would not. So you would expect to have something like vi vj proportional to delta ij, basically, so you would not see anything on average. But say vi squared could be non-zero. And some people have tried to do that, to use that, to create a primordial universe after a bounce. It's absolutely impossible after a phase of inflation, because inflation just dilutes everything away. But after a bounce, then you can use that to produce primordial magnetic fields. And so that's more a window of opportunity, as Robert liked to say. more than an issue for the bouncing situation. Well, how long do I have? Like 10 more minutes, 15 minutes? Or are people tired of hearing me? Okay, no response, so I will assume it's 15 more minutes.
You have 10 minutes, Patrick.
Okay. Well, I tried. Okay, so let me see. 10 more minutes. Hang on, what should I pick then? Yeah, well, no, I'm not going to do that. I was about to explain why, if you were concentrating to the ekpyrotic phase, you can calculate thing in the ekpyrotic. Well, you do that briefly, sketch it. In the ekpyrotic phase, when you're having only the exponential potential, because you would be tempted to say, well, maybe I can use the ekpyrotic phase to produce my initial perturbations. If I do that, as I said, I actually have Z proportional. You remember the ekpyrotic potential was V minus V0 exponential minus 2 over Q phi, right? So I have V, I have Z now equals minus eta in the contracting phase, Q over 1 minus Q. And that gives you Z double prime of a Z equals, just to write it down, Q to Q minus 1 over Q minus 1 squared eta squared. So you see now you're having a 1 over eta squared, and you can solve, because this potential is exactly solvable as far as the equation of perturbation is concerned. You end up with Bessel functions and things. And in the long wavelength regime, what you find in this case is that P zeta, zeta of K now is proportional to K to the 2, sorry, that's 2 minus 3Q divided by 1 minus Q. And what you find is that NS minus 1 is, roughly speaking, 4 minus 2Q. So this is a very deep blue spectrum. And that explains why you need to have an extra component. You cannot use the ekpyrotic contraction to produce a scale invariant spectrum. So you must manage your model in such a way that you first produce the spectrum on sufficiently long wavelengths, then you enter the ekpyrotic regime. And so the ekpyrotic regime will produce n equals 4, and well, sorry, n equal 5 actually. Very deep blue spectrum, but you're not interested in these wavelengths. And so that's why you need to do all these complicated issues. It's not as simple, I must say, as inflation. So in fact, so as I was just saying, so in order to have a viable bounce model, well, first you need ekpyrosis or something similar to remove the shear, as I was saying. And you need other perturbations. As far as we know, if you get rid of ekpyrosis, basically you will always have something similar to that, and you will always have like Q much less than 1. You will always have such a parameter that NS minus 1 will read like that, and you always end up with a very deep blue spectrum only with ekpyrosis. So you need an extra perturbation matter contribution for perturbation. So that gives you, so you have various possibilities for that. As I was saying, you can have the matter contraction, as I was just referring to earlier, with its issues. But then you can say, okay, well, I have this ekpyrotic contraction, but I can mix it with something else, you know? And then, as Sriram was mentioning earlier, you can do that with 2 fields. So if you have 2 fields, of course, you will produce isocurvature, which has to be removed again because you don't observe it. But then you can use that, again, as a chance rather than a caveat. You can use it by using the curvature mechanism. and solve the thing. It's not very well working, but it's you can do that as well. Now, as I was saying here, you have a growing mode and a decaying mode. And when you reach the bounce itself, which is very often the maximum of this potential, or it's not necessarily the case. So this is the usual case which you have in inflation. In bouncing scenarios, that can be kind of bizarre. You can have various possibilities for z over z double prime over z. So it's really not as simple. So basically what you have in general is the following. So when the scale factor goes to its minimum and you are already below the potential, right? So you have set your initial condition over there and you propagate them through. And so basically, you see you phi your, say, V or phi or whatever, I mean, whatever component of the perturbation curvature, if you're interested in, you should rather have that. So you have, as I said, you have two components, right? So you have the component, I should not have taken zeta because it's hard to write on. So let me stick to the bounding, the gravitational potential. So you have a growing mode here in the contracting phase and a decaying mode in the contracting phase. Now you go through and you end up with a growing mode in the expanding phase and a decaying mode in the expanding phase, right? And let's say that you're having a typical time here. And in between these two things, well, you will end up with a transfer matrix. And its shape is absolutely not obvious. And in fact, it looks like a TGG, depending on K, T, G, D. G and D means growing and decaying. All of these are depending of K. And nothing prevents you from having the ordinary. The usual in inflation is that you have this thing and you reach a plateau here, you reach a constant essentially. And this constant is actually already the dominant term that comes here. So the contracting mode, or the decaying mode decays, and it's the one you did not want. So actually it removes for you the mode which is not compatible with the data. But if you have a general matrix here, it may not be the case. Well, first of all, you can have a mixing between these two modes, which is already problematic. But not only that, it can also change the spectrum of the modes. And there are models for which this happens. So in fact, this is extremely model dependent. And we don't have, contrary to the case of inflation, you see in inflation, you have the so-called slow roll thing. So you have slow roll parameters, and they're not really very much model. I mean, the parameters themselves are model dependent, but you have slow roll parameters, and they're small, and so they are small numbers. They don't depend on K and whatever. So you don't have these things. So the whole thing is not. You have generic predictions for inflationary single field inflationary scenarios. You don't even have that for that case. So you might. So I probably won't, no, I definitely don't have time to go into that. Still have a couple of more minutes, because you could think, well, okay, now I enter into this phase. I know that this is very well described by GR, say, and I know that here the expanding phase is also well described by GR. So of course, in the middle, as I discussed like for some hours now, in this regime, GR with ordinary matter is problematic. So how about using matching conditions and say, well, okay, I have like say minus eta star here, plus eta star here. And I say, well, okay, then I have this delta eta star. So I will identify this bit with this bit and see what happens. After all, it's fairly possible. And I could consider the option of using matching condition. You know, a la Israel, for instance. And so that has been proposed. And so one thing is that, of course, when you're matching, you're saying, I will match to the same point, right? So the scale factor will be like approximated by that, which is fine. But then immediately you find that the matching condition is telling you that the Hubble rate, plus or minus, this is the Hubble rate arriving here, the Hubble rate going out of there. You see that here the Hubble rate is negative, of course, because you're in the phase of contraction. And here it's positive because it's in a phase of expansion. So of course, it cannot be zero here. And it's actually a pressure term, which is completely arbitrary. And that may actually depend on K if you really want to do the thing for perturbations. So it's a completely arbitrary pressure, which you have no idea what it is. So in fact, your model dependent issue that was coming here is just merely reproduced here in the matching conditions. So you're essentially doomed. There's no way to do that. And okay, there were also some other issues with instabilities, as Sriram mentioned. There are also instabilities because you see when you're contracting with, when you're expanding something, basically, in general, the perturbations tend to go down. But of course, when you're contracting, it's the other way around. So basically, anything which starts growing grows more rather than decay. So you may have other problems. And in particular, for instance, this decaying mode, the usual decaying mode may end up being a growing mode and a much more growing than anything else, and eventually become unstable. And you can even have back reactions, and you can even have real problems. So in fact, I probably will have to conclude now after that's indeed an hour and a half. I plan to write something, but that's okay. If I want to conclude, I want to say that, okay, bouncing scenarios, they might provide an interesting interesting scenarios for cosmology. There are many issues, but they can solve the standard model problem. They don't create too many other problems. The only issue is that they're really, first, they are difficult to implement in GR, contrary to inflation. They're probably easier to implement in quantum gravity theories than inflation, but I don't know if it is good or bad. But they create a lot of new instability, like shear instability, vector instability, curvature instability during the phase of contraction and all that. So, but on the other hand, as I said, usually you quantize perturbation and not the background. And we can understand that it is complicated to have a theory with GR and produce a bounce. That probably means that if we want to use a bounce, we need to quantize the background as well as the perturbation, which in my view is more consistent anyway. So I can also imagine that we can see bouncing cosmologies and quantum bouncing cosmologies as test bed for theories, and in particular for quantum theory, in particular of gravity. And I think I will conclude with that. Thank you.
Thank you. Thank you very much, Patrick. Let me just see whether there are questions. Students, can you raise your hand so that I can unmute you and you can ask your question?
Maybe people are tired because it's 4 in the afternoon.
Are there any questions?
I think there may be something in the chat. I don't know.
I'm also looking at the Slack. Maybe they will add.
Yes, the Slack is. I had to disconnect it because it was sending me signals.
So, Patrick, so the status, if I can ask a couple of questions, the status is,
sure.
Do we have models where they track the perturbations across and evaluate the spectrum out on the other side of the bounce, post-bounce, I mean?
We can produce models, yes, of course. There are models. And, I think you should ask Robert that. He will tell you immediately that, yes, of course, you have such models. I also forgot to mention one thing is that, yes, you can have perturbations crossing the bounds and having a reasonable spectrum at the end, but then you also have to ensure that the non-Gaussianities are not exploding as well. Because you see all these instabilities, you have to tame them And it's not easy. And normally when you tame an instability, what you do is you just push it away somewhere else. And so very often what happens, that's why it's very complicated to build these series, but to build these scenarios. But what you're very often doing is that you tame the whole thing, everything is fine, you have a nice spectrum, and then all of a sudden when you calculate higher orders, you recover these instabilities, but now in the form of non-Gaussianity. So at the end of the day, that's why I also was saying in the first lecture that very often you just have issues with perturbation theories.
So the bottom line is that you may be able to construct models, bouncing models, which are consistent with, say, the CMB data, but at the level of power spectra, but non-Gaussianities may be large in such scenarios. That's the...
Yes, well, I would conclude rather that by saying that you probably can do everything properly and nicely, but you have to check it.
Okay.
You know, when you start with an ordinary, say, slow roll model of inflation, more often than not, you don't even have to bother about non-Gaussianities because you know almost from the start that they will be negligible. In this case, it's never obvious. I mean, if you take like the simplest possible model where you have, you know, a bounce with a scalar field with positive spatial curvature, you find that the non-Gaussianities are just tremendous. So you fit exactly the right spectrum, you do exactly right everything, but the non-Gaussianities are just exploding.
Very large.
Yeah, very, but I mean, very large, I mean like 10 to the 4 or something like that with respect to assuming that it's, you see.
I understand.
So it is complicated.
Okay. Patrick, I see no questions here. Maybe students will, you know, digest your lectures and come back with questions during the tutorial session.
Yeah.
Thank you for your lecture.